In this section, we're going to talk about different types of electrical current, what it means to change energy from one form into another, and we'll take a look at some technological devices that can do just that. Electrical energy has existed forever in the natural environment. When objects rub against each other, the friction can cause an electrical charge to build up, which we call static electricity. This happens in a big way when clouds rub against each other in the sky or against the ground, causing an imbalance of electrons. Eventually, if the charge grows big enough, it will balance out in a massive static discharge that we call lightning. The quickest way for electricity to balance out is to find its way to the ground. Electricity always wants to take the shortest possible path to the ground, which is why lightning normally strikes the tallest objects around. We see the same thing in a much smaller way when you shuffle across a carpeted floor in your socks and then touch a metal doorknob. The shuffling builds up a static charge, and touching the doorknob allows the electrons to flow from you back to the ground. Static electricity can be powerful, but it's also unpredictable, so it isn't very useful for us in technological devices. In order to make productive use of electricity, human beings invented current electricity, in which electricity is made to flow through a defined path called a circuit, and by carefully designing the circuit in different ways, we're able to get the electricity to power all kinds of useful devices. There are two kinds of electrical current. We call these direct current and alternating current. Direct current is current that flows through a circuit in one direction only. This is the kind of current required by most electrical appliances in your home. It's also the same type produced by batteries. However, one limit of direct current is that it doesn't travel well over long distances. A huge amount of electricity is lost if you try sending direct current far from its source. Alternating current is much better for traveling long distances, so this is typically what is used in long-distance power lines. With alternating current, a power plant can supply electricity to an enormous network of homes and businesses. We've talked about how natural static electricity can be unreliable, so we humans had to develop ways of creating electricity from other energy sources that we can control more easily. The law of conservation of energy states that energy cannot be created or destroyed, but it can change form. So we can't just whip up electrical energy from nothing. But we can start with a different form of energy and convert it into electricity with some clever technological tools. Other than electrical energy, the other major forms of energy in the universe are mechanical, chemical, and nuclear energy. Using different technological devices, we're able to convert between these different forms. We often hear about other forms of energy, but these are usually a version of the other four. For instance, sound and heat energy are really forms of mechanical energy, and magnetic energy is closely related to electrical energy, as we will see. One device that converts between energy forms is a battery. A battery converts chemical energy into electrical energy. Different batteries use different chemicals to make the reaction happen, but all batteries contain chemicals which react together to produce an electrical charge. Batteries are usually marked with a plus symbol at one end and a minus symbol at the other, indicating which side has a negative charge and which side has a positive charge. If a conductor, such as a copper wire, is used to connect these two sides, then electricity will flow from the negative side to the positive side. Eventually, the chemicals inside the battery will have completely reacted with each other, and they will no longer produce an electrical charge, so electricity stops flowing. We call this a dead battery. Certain chemical combinations allow the battery to be recharged. So in things like car batteries or cell phone batteries, the process can run in reverse. Electrical energy is added to the battery from an outside source, like a wall outlet, and the chemicals in the battery re-separate so they can begin the process all over again. Another device that can convert energy from one form into another is a generator. Generators convert mechanical energy, or the energy of motion, into electricity. Basically, anything that moves can be used to power a generator. Many houses have personal backup generators to keep their electricity going during storms when the power goes out. These devices use mechanical energy from an engine to turn the generator and make electricity, and the engine gets its mechanical energy by converting the chemical energy from gasoline. Generators can also be found in wind turbines, which use the mechanical energy of the wind flowing over the blades to turn a generator and produce electricity. The electricity from a generator can be stored in batteries as chemical energy and then used later. This is what happens under the hood of a car. Cars have their own little generators on board called alternators. Some of the mechanical energy from the car's engine is used to turn the alternator, which generates electricity to recharge the car's battery while driving. This is why car batteries can last so long without dying, because they're being recharged by the alternator all the time the engine is running. This is also why the car's battery dies when the engine is off, but the battery is still being used for lights, heat, AC, or the radio. The battery isn't being recharged unless the engine is running. Big or small, generators all work by the same principle, and it relies on the relationship between electricity and magnetism. A funny thing happens when a magnet passes a coil of conductive wire. The magnetic field causes electricity to start flowing through the wire. So by mechanically spinning a magnet many times very fast near a coil of wire, we're able to produce a strong, continuous flow of electricity. All we need is a source of mechanical energy to spin the magnet, like the energy from the wind, running water, a car's engine, or human power. Motors are sort of the opposite of generators. Where a generator turns mechanical energy into electrical energy, motors turn electrical energy into mechanical energy. Pretty much any electrical device that moves uses motors. They could be tiny like the motor used to move the hands on a clock, or more powerful like the motor in an electric car or the motors that control a robotic arm in a factory. An electric fan is really the opposite of a wind turbine. A wind turbine uses wind to turn a generator to create electricity, and a fan uses electricity to turn a motor to create wind. Normally, a plain old wire wouldn't be magnetic, but when an electrical current runs through the wire, it gets a magnetic field just like a magnet. If you've ever played around with magnets, then you know that magnets can be made to push away from each other with a physical force. This is what is going on inside a motor. Electricity runs through a wire to create a magnetic field. This magnetic field pushes off from another magnet and causes it to spin. This spinning is mechanical energy that can be used to power just about anything if the force is strong enough. A magnet is a piece of iron with an atomic structure that pushes or pulls on other magnetic substances. When we talk about magnetism, we're talking about creating or manipulating the magnetic field around an object, the way we do in motors and generators. Magnets are useful, but sometimes it's more useful to have a magnet that can be turned on and off. This is called an electromagnet. By running an electrical current through a wire, the wire can become magnetic, and when the electricity is turned off, the magnet is turned off too. Electromagnets are the basic principle behind all kinds of technology, like high-speed trains, digital recording and storage, and recycling technology. This relationship between electricity and magnetism is what makes countless pieces of technology possible. Generators use motion and magnetism to create electricity. Electromagnets use electricity to create a magnet, and motors use electricity and magnetism to create motion. If we take a look at the inner workings of a power plant, we can see how our electricity is born. Every power plant needs an energy source to begin the process. In the United States, the most commonly used fuel for electricity is coal. First, the coal is burned, and the heat from the burning coal is used to turn water into high-pressure steam. The steam is used to spin a turbine, and then it condenses back into water to go through the cycle again. The spinning turbine is connected to a generator, which produces electricity. The electricity is then sent down power lines to supply power to people that need it. Coal is relatively inexpensive and easy to find in the U.S., which makes it a logical choice as a power source. But burning coal can cause air pollution and other nasty environmental side effects. Coal is also a fossil fuel, which means that it takes millions of years to form, and we can't replace it. So once we run out of coal, it's gone. For these reasons, there's an increasing push to phase out coal as our main source of electrical energy and replace it with more sustainable technologies like wind, solar, and hydroelectric power.